In this lecture, we are going to focus on two instruction sets. The first one is RISC, or Reduced Instruction Set Computer, and the other is CISC, which stands for Complex Instruction Set Computer. But before we do that, let us first take a look at what an instruction is. So an instruction is a command given to the processor to perform an action. So an example of an instruction could be an add instruction, which tells the computer or processor to, suppose, for example, say add two numbers. Next we have instruction set. So an instruction set is the entire collection of instructions for a given processor. So suppose a processor may be able to execute a number of instructions. For instance, a processor may know how to add two numbers, how to subtract two numbers, and so on. So the collection of all the instructions that the processor is capable of executing is called the instruction set. So architecture. Well, the term architecture implies a particular way of building the system that makes the processor. Well, obviously, to be able to execute the instructions that I mentioned earlier, you need a processor, and how you build that processor is called the architecture. Okay, so before we discuss in detail about today's topics, let us first again recap that a computer is capable of understanding only zeros and ones. It does not understand the code that you write in a high-level language such as C, where, say, suppose you may write something like int C equals A plus B. Obviously, your computer does not understand this. It only is capable of understanding zeros and ones. So what happened in the early days is that programmers used to write programs in machine code. That is, they would write programs like this. Basically, there would be a set of instructions written in machine code, and machine code, as you can already tell, consists of only zeros and ones. So the way they wrote these programs is that basically there were switches. So basically a 0 would mean that a particular switch was closed, and a 1 would mean that a particular switch basically a 0 would mean that a particular switch was open, and a 1 would mean that a particular switch was closed. So as you can tell, that this was pretty gruesome, and it was very difficult to program back in the days. So to make things easier, assembly language was invented. So assembly language is basically a higher level form of machine code. Basically, assembly language is machine code that is human readable. So suppose an assembly language program for adding two numbers would look something like, say, this. So we'll later take a look at what these dollar symbols mean and everything. But basically, assembly language was invented which was basically a human readable version of machine code, and it made programming even easier. So afterwards, an even higher level forms of programming language was invented. So from this we have, say, suppose a programming language such as C, Fortran, etc. So now the question is, suppose when you write a high-level programming language, such as something in C, how does your computer actually execute the code? Obviously, your computer only understands, or your processor only understands, zeros and ones. So what happens is that when you write your program in C or any other high-level language, it is passed on to what is known as a compiler. So what the compiler does is that it converts this or translates this high-level programming language to assembly language. So you see, previously we talked about assembly language here, which is basically a human readable version of machine code. But we are not done here yet, since your processor is not capable of understanding assembly language. So the assembly language is further passed on to what is known as an assembler. So an assembler is a program that converts your assembly language into machine code, which basically consists of only zeros and ones. And that is what your computer is capable of understanding. So, and another thing that I'd like to mention before I start today's lecture, since we'll have to use this concept, is that suppose this is your CPU, right? Suppose this block is your CPU. Your CPU has some extremely fast memory units, which are known as registers. So your CPU has a number of this, and from the memory hierarchy lecture, if you remember, we mentioned that registers were the fastest form of memory. They had the highest speed. So now let us first take a look at the complex instruction set computer. So suppose you have a memory here. This is your memory. So in your within your memory you have addressable blocks. Suppose the address of this location is suppose x04, and the address of this location is suppose say x08, right? And within these addresses are the values, suppose 6 and 5. Okay, so suppose you want to multiply two numbers. Basically you want to multiply a into b. Suppose within a is the value 6 and within b is the value 5, right? So this is your target. So within the complex instruction set computer, this would look something like this: mult x04 x08. Basically x04 is the memory address which contains 6. In other words, x04 is a here, and again x08 is the memory address here which contained 5. In other words, x08 is b here. So just to make things clear, the line of code that I wrote here is a high level programming language. So example C, and this is what your complex instruction set, a typical complex instruction set computer would have an equivalent instruction for the high level programming language code that I wrote earlier. So what happens is that when you're so there is one thing that, so afterwards let us talk about the result. So in your high level programming language, you're supposed to store the result in C, right? So suppose so for simplicity's sake, let us say you wanted to store the result back in A. Okay, so what your program would do, what your complex instruction set computer would do is that initially it loads the values from x04 and x08 memory locations where 6 and 5 respectively were present. It would then multiply those values. The result would be 30, and this result would get stored back to A. So A was x04, this memory location. so it would get stored back to this memory location. So your 6 now would be replaced with 30. Okay, so this is basically what a typical complex instruction set computer instruction looks like. Basically what a CISC instruction looks like. So within one instruction, as you can see, you are actually executing a lot of things. So now let's take a look at the same code, how the same code would look like in our RISC architecture. So I'll draw the memory, I'll just copy paste the memory from here. So I think this won't do, so I'll just write everything from scratch. So let's say you have the same memory as previously. Suppose you have addressable spaces within your memory. This is x04 and this is x08, and it contains the values 6 and 5 respectively. Okay, so for RISC instruction, the philosophy is that you want to break down your instructions into as simple bits of code as you can. So the CISC instruction that I talked about earlier is called complex because this one line of code is actually doing a lot of things. It is first loading the values from memory, then multiplying them, then storing the values in memory. So one single line is doing a lot of things, whereas with RISC, which we are going to take a look at now, which stands for Reduced Instruction Set Computer, it is actually a breakdown of multiple instructions. So let's see. So with CISC, you'd have to first load the data from memory yourself. So you do this using something like, say, instructions such as load. So remember, previously I talked about registers, that your CPU has some extremely fast memory units called register. So suppose this is your CPU, and within here is your register file, and it contains registers. Suppose there are multiple registers. I'm going to name this, suppose $7, suppose this is the 7th register, and $8, suppose this is the 8th register. Okay, so with RISC approach, what you're going to need to do is specify the register in which you want to load this memory value to. So basically what I'm trying to say is that you have to specify in which of the registers you want to load this value 6 to. So suppose I want to load the value of 6 in register 7. Please load the value which is in x04 address to my register which is $7. So again I have to do a similar thing for the value of 5 which is in address x08. So if I want to store 5 here, I would need to write something like this: load $8 x08. So basically it means that load the contents of memory address x08 into $8 register. So basically the same thing was happening in the CISC instruction as well, but it was all being done on its own. You did not have to take care of this. CISC was doing all of these things within one single instruction. So basically you cannot directly carry out operations on memory address on the memory. You have to first load them into a register which is inside your CPU or processor. So then you would finally carry out the operation. So let's say the multiplication operation for RISC stands for prod, or product in short. So suppose I want to multiply the contents of $7 register with the contents of $8 register. So basically this in turn would multiply 6 into 5 into 30, and you can think of it like this, that this sentence, this line of code translates into something like this, that the contents of $8 is being multiplied with the contents of $7, and the result is being stored in $7. So basically after this instruction is executed, $7 would no longer have 6, instead it would have 30. Okay, so now remember we had to store the resultant value to memory x04 as well, right? So with RISC you have to do this yourself as well, using suppose something like store. So again, where are we storing the value? It's in x04. So let's write x04 memory address followed by the register which contains the value that we want to store, which in this case is $7. So $7 here now contains 30. So as you can see, the same instruction which is in RISC takes 4 lines of code, whereas with CISC it was just 1 line. So now if we want to talk about the differences between a CISC, so let's just write differences here between a CISC and the RISC approach. The first difference that we can point out is that CISC makes compilers job easy. So as you can see, so this was our high-level programming language, right? And I mentioned before that your high-level programming language has to be what? Converted to assembly language by a compiler. So to convert this high-level programming language into assembly language, you can see that both of this look pretty much the same. They share a lot of similarities. So with CISC, your compiler does not have to do much work to convert a high-level programming language to a low-level programming language. On the other hand, now if we come to CISC, RISC, so as you can see, this line of code has to be converted into 4 different lines of code that's in here. So obviously converting this single line of code to these 4 different lines is a much more difficult task. So in that sense, writing a compiler for a reduced instruction set computer is more difficult. Or you can say, in other words, that a compiler has to do more work to convert a high-level programming language to a RISC-based instruction set assembly language. So that's the first difference that I'm pointing out. So again, another thing that I'm going to point out is that with RISC, your instruction size is fixed, whereas with CISC it is variable. So what do I mean by instruction size? Well, basically by instruction size I mean the size of these instructions in bits. So we are going to learn about a specific MIPS, which is a RISC-based assembly language, and in MIPS every instruction is 32 bits. So this load instruction is 32 bits, this instruction which multiplies two numbers is 32 bits, this store instruction is 32 bits. Whereas with the CISC approach, your instruction sizes are not fixed. Suppose this multi-instruction may be 64 bits, an addition instruction may be 32 bits, and so on. So these are arbitrarily examples that I'm giving, but overall with CISC your instruction size is variable, whereas with RISC the instruction size is fixed. Okay, so now let's move on to another difference, which is instruction space. Basically, RISC consumes more memory. So what do I mean by this? Well, as you can see, with CISC you have to store just one instruction in memory to be able to perform a multiplication operation, whereas with RISC, to be able to perform the same multiplication operation you have to store 4 different instructions. So storing instruction consumes memory, and therefore RISC consumes more memory, whereas CISC consumes less memory. Okay. So another major difference is that with RISC, every instruction takes 1 clock cycle to execute. So clock cycle basically means the amount of time taken between 2 pulses of an oscillator. So we'll talk about clock cycle and clock speed in later chapters. Okay. So another thing to note here is that with CISC, once this instruction is done executing, so as you can see, this instruction was storing the value in a specific register. So with CISC, there was no need to specify which register that the result was being stored. So for the sake of consistency, let's say with CISC, the result, which is 3030, was being stored in register 7. But once this instruction completes execution, the value that was stored in register 7 is erased. So as you can see, if you somehow, your next line of code was something like this: A equals, okay, let's call this instead, let's call this A equals A plus B. So A now should have the value of the previous product of A into B. But as you can see, you'd now again have to load this value from memory, which is in X04 location. Well, obviously you would not have to specify this, because your in a CISC approach, your computer or processor would do this on its own. But the important thing to note here is that your processor would be carrying out an additional instruction or carrying out an additional task that it would have not otherwise needed if this value was not erased. But with RISC, as you can see, if you have the same instruction, that so we had initially A into B, and then if we have A plus B, with CISC, the value that you had stored in $7 register when you carried out this instruction is not erased, it's still there. So what you can do is that you can reuse this value instead of having to reload it from memory. So with RISC, it's more efficient when you have recurring variables in your lines of code. So that is another difference. So the summary is that CISC attempts to reduce instructions. However, with CISC, a single instruction may take multiple clock cycles. So I'm writing clock cycles with CC. Whereas with RISC, so by reduce instructions, I meant that minimize instructions. So with RISC, it's the opposite. It reduces clock cycles at the expense of instructions. So now, if you're curious, you may be wondering, which of these instruction sets do I use in my computer? Well, so let's talk about it briefly then. So CISC was the first instruction set computer, and after that RISC was developed. So on top of CISC was a platform developed called x86, which was basically developed by Intel. So the x86 platform is now currently being used by Intel and AMD as well. So as you can tell, Intel and AMD processors are in our PCs, right? In servers, etc. So, and on top of RISC, a platform called Advanced RISC Machines, or ARM, was built. So companies that design ARM chips include Qualcomm, Samsung, Apple, etc. And if you're familiar with these names, you know that they create smartphone chips. So RISC based chips or ARM based chips are present in embedded systems, such as, for example, in your smart TV or your smartphone, or for example it could be a Raspberry Pi as well. But however, if you say that x86 is entirely RISC based and ARM is x86 is entirely CISC based and ARM is entirely RISC based, you'd be wrong, because over the years these two platforms have borrowed from the overlying instruction sets. So basically what I'm trying to say is that x86 has borrowed some properties from RISC, as well as at the same time ARM has borrowed some properties from CISC. So you see, with the release of the Intel Pentium Pro processors, Intel introduced something called micro operations. So basically what micro operations does is it breaks a single instruction into multiple smaller bits, basically smaller instructions. So this does not look like the smartest way to write smaller instructions, but whatever. So as you can tell, this is quite similar to what RISC uses, right? And at the same time, in 2019, basically last year, ARM introduced a new design which had over 100 new instructions. So if you actually group them together, things kind of don't stay simple anymore. So over the years, these two platforms, x86 and ARM, has actually borrowed a lot from the upper two architectures, upper two instruction sets. So now you may be thinking that, oh, so x86 is basically for things that require a lot of computational horsepower, whereas ARM is just for smaller, low-powered systems, right? Well, if you're thinking about that, you have a wrong conception, because currently the world's fastest supercomputer, you can see where I'm going with this, the world's fastest supercomputer is ARM based. So ARM is actually not just for smartphones and embedded systems. ARM can actually be used for things that require a lot of computational horsepower or prowess. So furthermore, one of the biggest companies in the world, Apple, is now moving away from the tradition of using x86 processors in computers. So Apple is now going to manufacture their own ARM based systems, and they are going to put them in their iMacs, MacBooks, etc. So as you can see, technology has evolved quite a lot lately, and ARM nowadays, it is not just for low powered systems. Instead, it is a very viable solution for not only mainstream computing but also for intensive work such as servers as well as supercomputers. So overall, this was a brief introduction to reduced instruction set computer and complex instruction set computer. In other words, RISC and CISC.